So let me introduce Professor Flavia Rodrigues. I try to read some of them, okay? I know there's a very big CV, okay? Professor Rodrigues, I think this is very humble also. I know that the CV is more greater than that, okay? So Professor Rodrigues, I just opened the what the few words that she write about there, but I know that she has a lot to write here. So Professor Rodrigues, she is an assistant professor and postgraduate program in dentistry in UNIP from Brazil, and also she is an honorary assistant professor in the University of Hong Kong. She graduated from dentistry, and she has a master's degree also from engineering in São Paulo in Brazil. Her PhD is in biomaterial sciences. Also, she developed postdoctoral projects in King's College London, and also she has a very good link with the University of Birmingham, UK. She is have a 12 years experience, okay, in finite element tests, and I think we all of us are, especially from research point of view, and all the attendants here are. It's very important for us. She wrote a lot of manuscript. She is a reviewer in a lot of things. She is also a founder of a program, research programs. So I wouldn't like to take a lot, Professor Rodrigues. So I will give the mic for you. Thank you very much. And we are all willing to listen to this very, very important contribution. Thank you.
Thank you very much, Hamdi. So good afternoon to everyone. I'm really, really happy to be here today because I've been in your place before, not in your city, but in Egypt, and I felt in love with the place and people. So I'm really honored, and I couldn't say no for this invitation at all. So thank you very much for that, and thanks for all your organization, and thanks for your Dean and Vice Dean speeches as well. I felt really touched by what they said.
Thank you.
So I'm gonna share my screen now. It might have a little bit of delay.
No problem.
So you guys just give me a feedback if you.
Sound, please, Professor. Sound. Professor Rodrigues, I think you need to open the mic again, please. Professor.
I don't see her on the screen, Professor Hamdi.
Yeah. I think Professor Flavia, Professor Rodrigues, please.
Yeah, do it again.
Yes, please. Yes, please. Open your mic and camera as well, because I think we have a problem. Yeah.
All right. For me, it appears it's open, so I'm trying again.
Now I think we can see your screen now. Yes.
Okay. So when I shared, my video closed automatically, and then I don't have access anymore to open it.
I will try to open it again.
Yeah, feel free to open it if you want.
I will. Just a moment, please. Just give me a second. Just I will do it.
No problem.
Have a bit delay. It have a bit delay.
Mm-hmm. So can you see my slide?
You can start, and I will try to do it.
Okay, you can see my slide?
Yes, we can see your slides.
All right, so we can start. The slides are more important than me, so don't worry. So I was invited by Hamdi to talk about finite element analysis and finite element methods. And we are discussing how it could be interesting for the audience we have here, because it's a mixed and broad audience. So I hope you like what we've selected for you today. So this lecture is divided by 3 parts. First part, I will share a little bit about me. So talk about my home, my uni, and my career very quickly. And then basic FE concepts that's more important than me, and applications that might be even more important and interesting for you guys than the other 2 items. So starting from myself, I've been in Egypt in December 2018 and January 2019. So I was there for the new year. So you can see from my pictures how happy I was to be there. So this is Cairo, of course, and Alexandria and Luxor. And the best part of my trip was when I was meeting Dr. Elham Falsi. I'm not sure if I am saying her name correctly. Yeah, but it was really like the best part of the trip, because when you meet good people and you can make good connections, this can be in your memory for much longer time than just pictures and landscape, although they're amazing. And a little bit of my hometown. I live in a city called Indaiatuba. It's based on the state of São Paulo, so it's exactly here. So this is a picture of the main part of the city. So you can see there's a lot of green area in there, which is a little bit different from the way I work. So you're going to see. So for the ones who are not familiar with the size of Brazil, just to mention that we can fit the whole Europe or almost the whole Europe and still have some spare room for some other countries to get in. So it's really a continental size of country. And this is the picture where my university is based. So this is São Paulo, the capital of the state of São Paulo. So you can see we try to put some green around, but the ocean of buildings, you actually can see no end, because they really have no end. So we are talking about a 20 million people city. And
but I like the bridge. The bridge is amazing.
Yeah, I like it too. Yeah, and I'm very lucky that I passed through the bridge to reach the university. So that's a good sign off. And just to mention the size of the city in terms of population and so on, it's like the UK or even a little bit more. So here is a picture of the university, but our university is spread out around the city. So I couldn't have a picture of every single unit we have distributed here. But this one is actually the building I am based. So we have another one just across the street, which is the dental school. And there is another one around here that it's the lab. So this building is just the postgrad classrooms. And there is just one lab that is the 3D printing lab, but all the labs are in 4 other houses on the other side of the street. So you are more than welcome to visit us anytime. About my career, of course, Hamdi has already talked, so I'm gonna go really fast here. So I am a dentist, but I did my master's in mechanical engineering because I knew already I wanted to work with materials. Then I moved my PhD to biomaterials in dentistry to join these 2 things. And half of it I've done in Manchester. After my defense, I went to a university that I'm not in anymore because now I am at Univ. But at that time, I also did my postdocs in Birmingham, and also King's College was just some projects that I did in FE for them. Then after being in Birmingham, I was with such an open mind that I was in contact with British Council Brazil, Uruguay, and the Australian Embassy Department of Education. And I started being involved with coaching and mentoring training for students, for professors, mainly academics, in scientific communication and academic writing. And from that, I got involved with other two universities, one in Brazil, the Hong Kong. I've opened my own business. I continue to work for Birmingham, and I've got a consultancy kind of position in Vitae. So it's still what I do. And because I'm curious and I still want to keep helping people and join my passions, I decided to open a business to help companies to move forward in the way they communicate and they work with teams and get more productive. And my current project now is to open a tea business where I can join research, teaching, and my passion for tea. So moving to our second topic, which is the topic of the lecture, we have to talk about finite element method, but mainly what is it about? So I know that many of you just heard the name of it, but have never been touched by doing a model. So there are some basic concepts I would like to tell you, and then you can follow the rest of the lecture. So when you have any type of model, so a model is a structure that you divide in small pieces to calculate displacements, tensions, stress, strain after the analysis. So for each of these geometry, that can be a triangle, can be a tetrahedral, can be an hexahedral, and any other, you have what we call element, which can be 1D, 2D, 3D, depend on the shape of it. And all the corners, the vertices, they're gonna have a node. And some of them, you can see they have a node in between of the side of the geometry. So the elements will be the entities that are going to carry the information of the materials that we are going to input in the software. So it can be the elastic modulus, it can be coefficient of friction and so on, Poisson's ratio as well. And then after you do this in the software, these elements are going to transfer and translate what you've put in there to the nodes. And then after the analysis, you're going to have that graphic is in colors, or you can select a current Y and X graphic to show what happened in a certain line or in a certain curve, specifically from the geometry. You're going to be more familiar with that and other next slides ahead. So, of course, we cannot leave all the mathematics behind today, but of course, I've brought only what I think it's going to be useful for you guys. So we have an equation to describe the behavior of a line, and we have an equation to describe the behavior of, for example, a parabola. So if we bear in mind that this curve, this parabola, it's actually representing what's happening in the reality, we call it analytical solution or analytical result of the problem we are facing. So what FE does is actually a discretization of a model. So when we go to the geometry and divide that geometry in many small pieces, as I did like here, okay, I divided this geometry in elements. So what I'm doing is actually a discretization. So I divide the problem in a certain amount of elements. And this is why the method is called finite element analysis, because it has to be a finite amount. Otherwise, I will never get a solution. I will be dividing, and never get to anywhere, okay? So you know you can divide this in infinite amount of points, but you will never get what you want as an answer from the question you've made. So just to exemplify, if I have a problem in FE and I want to reach this point, if I use 2 elements, like 1 and 2, this solution is not the same as this. So it's showing me that I need to do more discretization. So if I use 3 elements, like 1, 2, 3, it's better than this. I'm getting closer. If I use 4, 5, 6, and then so on, if I use 10, for example, I'm very, very close to this one. But when to stop? When we decided how can we stop? Otherwise, you're going to be doing, as I said, infinite and not finite. So you have to do what we call mesh convergence study. So you run your model and you see the results you are looking at. When you move the number of elements in the mesh and you start getting the same result of your problem, then you are okay. You can stop and you can keep this one rather than this one, because then your computer is not going to suffer a lot to process the problem. So an example here, this is a really fresh example from 2 days ago. One of my students is working on this model. So he was showing me that, okay, Fla, we finished the geometry of these tools. He's mimicking here cervical carious lesion, non-carious lesion, and then the periodontal ligament. So this is how the screen appears to people who are working with the software. So you have to create the model, inputting information from geometry, materials, you do the mesh, so many things like in tables like these, you just input the values here. Many of these values you have to bring from the lab condition, and then you input in the software to make it more close to the reality. So here, that's André Souza and Matheus Araújo. André is a professor in one of the universities in the north of Brazil, and I'm supervising him in this project with Alexandre from São José dos Campos, the southeast of Brazil as well. So Alexandre is a super expert in FE as well. And 2 days ago, they are showing us the discretization of this model, and we are like, yes, you got it. So it's a really important step for the ones working with FE, because it's a very difficult thing to do. It's very time consuming. So we are all celebrating that we could make it. So you can see here the discretization. But of course, this was the last step. The real model is going to have a fewer amount of elements. So in terms of the analysis, you're going to see many papers, they say the analysis, the FE analysis can be linear or non-linear. So basically, when you say it's linear, the stimulus intensity you are putting in the model has to be proportional to the effect at the structure that received the stimulus. So we're going to follow what we call the Hooke's law. It's going to be always a linear behavior. Okay, so for example, tension equals to elasticity, so the modulus of elasticity multiplied by the deformation. Okay, so Hooke's law says that when you have a force, it's equals to a gradient that is unique, and then the extension of the spring, because he developed this theory by using springs. So it's barely saying that if you unload this, it's gonna be returned in the same line. In this case, if you unload this behavior, it doesn't necessarily comes in the same way. It can come like this, it can come like this, it can come very close, but never the same as this. And then we have a non-linear behavior. For example, we have as a non-linear situations where we want to simulate contact between 2 different bodies, for example, restoration and the adhesive layer post in an after endodontic treatment with the cement and with the denting. So this is basically a non-linear behavior. So in terms of the steps, we have 2 big steps here. We have the pre-processing and the post-processing. The pre-processing, when you read in a paper that people were doing the pre-processing, they're actually doing the build of the geometry, the mesh, which is the discretization I explained, the boundary conditions, which is the moment where we input and create, for example, the load condition, the temperature condition, shrinkage stress, any temperature or structure behavior that we want to input in the model. Then we move for materials, where we are gonna create the materials like resin, denting, enamel, restoration, and all this, root canals, anything that you want, bone, for example, anything that you want people to understand that it's included. And then in the property steps, you have to create the properties, input the properties, and link to the materials you create. So the model will not run, will not process if you create a material and there is no link to the properties, and the other way around as well. If you create a property and you don't create the material, link it to this property. After all the pre-processing ready, you go for the post-processing and you go through the analysis and you get your results that usually you return for the same software you did the pre-processing to check the results. So one thing it's important for you as a researcher as well is that FE, there's a lot of states in your simulation, but you need to bear in mind that there are uncertainty in these processes. So as you saw in the parabola, we will never get a very perfect parabola as the analytical solution, as the reality, but we can go very, very close. And my concern as an FE person, a researcher, is that I see many papers that I review that people care a lot about how the model looks like and the mesh looks really refined, and they don't take care a lot of the most important part, where we actually can have a lot of errors and uncertainties. So load values, supports, how they are fixed, contacts, gaps, all of these will generate much more mistakes if they are far from the reality, rather than these parts and these parts. Okay? So there are many checkings in the software we have to do. It would be an 8-hour. What I want to show is really like, do you really need a 3D model to answer your question? Do you really need thousands and thousands of elements to answer your question? So really check all these if you are going in a right direction. And also, there has to be also always a balance between the stress distribution and the strength distribution. So when X is higher than Y, the failure is going to occur, and the higher it is, the higher it's going to be the failure. So if you know this before your simulation, you can avoid many mistakes on it. Also, I need you today to know the difference between stress and strain. So stress is the restoring or deforming force per unit of area. And the strain is more related to the shape of the object we are going to study. So the formulas are a little bit different here. And the units also, because the strain has no unit, because we have millimeter and millimeter, so they cancel each other. So this is a really important information that people really ignore. Many people think that if you know how to play video games and Legos, you are able to work with FE, because they kind of look like the same. However, even ISO requires officially a lot of experience for you, depending on what you're simulating. So we need, for example, to simulate a plane that's going to travel people from Brazil to Egypt. We need to have a plane that it's going to have no failure when it's flying. And it's able to have 250 people on board. So it's a VTOL experience. So the person simulating this needs at least 5 years of engineering experience and at least 6 months of finite element experience after a formal training. And a formal training can be 1, 2, 3, 4, 5 years. So this is something that I would like you to think carefully when you read papers from groups that do FE, and also when you ask people to do FE with you and for you. So going to the third part, we are going to the applications now. We could spend 20 hours today just showing applications to you, but we've selected some of what we think is the current most attractive topics. So here is the QR code for you that Hamdi asked me to include to make sure you're going to receive your certificates for this lecture. So I'd like to ask you please to close your microphones because I'm having interference. Okay, thank you. So I'd like you to introduce Professor Alexandre Borges. So his name is here, Alexandre Luis Souto Borges. He is the leader of one of the groups in Brazil that do a lot of FE work. And because I know him and I know the university and the group since I was born, actually, I really, really trust on his work. I've been following his work for many years up to now. So this is why he is the one helping my students when we are doing a more complex model. So I've brought here some of his recent papers, but he has like loads and loads in FE, so you can explore by searching his name. And I've decided to show some of, I think it's very interesting for you, with very useful information. So this one has a question. So does overlay preparation design affect polymerization shrinkage stress distribution? So it's an FE study. So what he did, he used an impression, unprepared tools, and assemble model. He works with ANSYS as a software in case you need to know which program, which software we are using. So he built three different preparations with different type of retentions. So I'm sure there are many clinicians in the audience, so I'm sure you can recognize the type of preparations here. You might have been doing some of them at the clinics. And clearly what we can see, it's the scale here, so we go for the cold color with lower stress and the hot colors for high stress. So you can see the more retention you have in a preparation, more stresses you have in the structure. So you don't have that much retention here, and you can see you don't have that much tension, stress generated, okay? And here you have what we call maximum principal stress is tensile stress, which is actually the tension response for the detaching or any other type of failure of restorations. So here you can see from another angle, a lot of stress concentrated at the caval surface part, if you'd think it's a direct restoration, but it's indirect. And then just a little bit you have here close at the pulp wall, and it's more relied to the proximity you have with the pulp, because you have a different elastic modulus between these two forces, these two materials, sorry. So you will always have a little bit of stress concentration because of this difference. So it's very tiny in comparison to the other two ones. And here you can see the cement. You have very hot colors at the cement. So it's the part of this rehabilitation that it's suffering. But when you compare to the others, you can see a lot of release of stress because you have the yellowish here, and then you have more like orange, stronger in the other ones. Another thing that I can show you, he did a 3D modeling as well. And A is the glasionomer group with a glasionomer cement. the B plus composite. Okay, so you have glass ionomer below the composite restoration. Then he did a metallic post plus composite resin. And then he did a fiberglass post plus resin composite. And then he did a very just a composite resin group without any other interference. And then he applied a load. So this is a very common everyday clinical problem that we face. So firstly, he was showing the displacement and deformation of the part of the tools that is suffering more when the load is applied. And you can see that the Oscar goes to the glass ionomer plus the composite resin. And then the metal post is suffering a lot here. It's giving a lot of displacement for this cusp. And we know that the displacement in premolar, depending on the magnitude of it, can really lead to fracture of one of the cusps after fatigue loading. And then here you can see the maximum principal stress. So it's tensile when you remove the restoration. So now you are just seeing the tissue, the denting for the same groups. So you can see just because of the difference of the elastic modulus, you see these red ones, that it's the same for all of them. But you can look at the pulpal wall, that here you have lower stress again. So again, the Oscar goes to glass ionomer and then resin. And you can see here from the other angle how much tension you are bringing when you are using a metal post. You are bringing not only to the post itself, but you can bring in stress for one of the angles here, and also look at here. So it's not just the tissues close to the post that is suffering, but also because of the displacements you are having here. So you have more displacement here because you can see the stress here as well. So the same with the fiber post. A little bit lower, but you still have it. And you have the green here going to the yellow. There's a little bit of yellow here. So you are still in a very careful region where failures can occur. And also when you don't do anything and just put the composite, because of the difference on elastic modulus, you can have a concentration here. And because of shrinkage, you might have this yellowish here. So here you have a little bit of yellowish. Then you have a very tiny red point here. So you have a different material with a different elastic modulus here. So it's expected that you have some disturb at the interface. But again, the Oscar goes to the glass ionomer group. So here you just see the composite and you can see how similar it shows. So really the difference between what happened in these groups is relied on the substrate rather than the resin. So as a conclusion of this work, he said that there is no mechanical advantage in using intraradicular pulse when an endodontically treated premolar requires an MOD. Filling the pulp chamber with glass ionomer cement and restoring the tools with only composite resin showed the most promising results in terms of cusp deflection and failure load and stress distribution. Then we have another group here in Brazil as well. Professor Oli was showing one of his work talking about incremental filling with using bulk filling, and also he published a lot in terms of bulk filling materials and the way you should use it in a cavity. So I've selected some other to show because he has around 400 publications in FE, so that's a really strong group here. So he was studying the effect of lutting materials, presence of tooth preparation, and functional loading on stress distribution on ceramic laminate veneers. So as you can see, there was no need for a complex 3D model. They are using a 2D model. However, the boundary conditions, the conditions he was using to input the information in the model were really, really high level, really close to the reality. So here was his results, and the clinical implication of his results was that resin cements and flowable composite resins create similar stress conditions if used for luting cement laminate veneer. As omission of tooth preparation could cause clinical complications, minimal tooth preparation can be recommended as it does not cause a significant increase in stress concentration regardless of the luting material. So you can see here from different materials, Real-IX, Spiraling, Tetric and Flow, Alcen, veneer, how the stress appears, because this is just this tooth is in all the models, okay, but it's just the cut that is different in the way he is showing here. And also he was showing the shrinkage, contact, and final for each condition. So you can see when you just apply shrinkage, when you apply contact, and you apply shrinkage and contact, okay? So it can really make the laminate veneer to detach from the model, for example, and also in reality. Another really nice paper and line of research he explores a lot is about light curing. So he was selecting these commercial light curing units, so Valo, Blueface, Valo Cordless, and Elipar, and he was trying to capture how much of the light actually reaches the zone that you want to cure. So far, these were the best ones, but he was making the study with many others, as you can see. And he was relating the cost of these units with actually the efficiency. So he could conclude that, unfortunately, the most expensive ones were the ones that are actually delivering the job as they should in terms of the radiance that they deliver. And he calculated for each of them. So he also does a lot of study in trauma. And this one I've captured from his page. So this is why his comment is in Portuguese. But what he's saying is that you have this condition and you have the X-ray and you say, okay, I treat these and everything's going to be okay. And actually, the amount of stress that the other two tools that were not directly affected are getting at the root is really significant. So you need to observe the X-ray with a better and accurate eyes, because you might fix just these ones and just say to the patient, go home, it's okay. But after some years, you can find some reabsorption here, and you don't know why it's like that if you did everything right here. So just make sure you know now that a lot, really a lot, you can see the red, a lot of stress reach the other tools, the other teeth, sorry. Another simulation that is not from Brazil, it's from another group. It's from Aslan, I think, and Oskan. So I showed this work because I wanted to see the level of discretization that this model needed that is different from the previous one. Okay, so you don't need to simulate the whole mandible to really study this problem, okay? Because the problem is actually focused on one teeth, so you can just do a segment and inform to the software that, okay, there is more here of the same tissue, there is more there to the same tissue. And the software will understand in this way. Then they applied a load in a certain angle, and the three conditions they were simulating was about perforation. So there was a perforation in the middle, another one here, and another one there. And then they restored with different materials, with biodentin, MTA, and actually nothing. And what they've got as an answer was a really good answer from MTA. Okay. Unfortunately, they haven't done the scale in a different value. Otherwise, you could see more difference between them, among them, sorry. But it was possible numerically to define that the use of MTA and biodentin may reduce the risk of 24 potentially harmful stresses in root perforation regions. So it's a really nice approach that, you know, MTA is a very expensive material when we think about doing 300 samples in the lab. But by using FE, you can have a sense of how safe it is to use one or another material. So it's another type of use for FE. Another group that is the University of São Paulo, which I did my PhD. So this is my supervisor and my super first idol in the world. I'm glad to say that. Not everyone has a good experience with supervisors. I've learned a lot from mine, thanks gosh. So today they are the three main people working with FE in São Paulo. So this is what they have been doing now. They're focused more on orthodontics and also zirconia. And they have, of course, more publications than these ones, but these ones were like the recent ones. And my super first paper with them was to show how simple could be a model just like this to really study cases like the fractures, the root fracture caused by wedge effect. So it was my super first contact with FE, where I've learned that a model needs to go from geometry, then elements, then boundary conditions, then materials, then properties. Then I say, hey, software, I have everything, please take a look. And then the software answers, yes, you are ready to go to the analysis. And then you do the analysis and you get the results. And this is the solver, so the brain that solved all the equations that appear in this step in the software. So from this very simplistic model, we could be able to plot some vectors. And we knew that if the vector is big, red, and shows itself on the model in a 45 degrees angle, it's a disaster, okay? So we could actually analyze all these vectors and check in which condition we could have or predict a catastrophic failure, for example, in a root. Other simple models with big answers. We've done, when I was in Manchester, Nadia Erefet from Jordan, from Amman, she was doing some studies with zircatseram and catseram. And then David asked me to build a model for her condition. And then I was like, okay, it doesn't need to be a 3D because her reality is a model that was so thin that the thickness of it was not actually important for the solver to actually solve and understand the problem. So we've made a 2D with quadrilateral elements. We've applied the load on the same region she was applying experimentally. And then we calculate the ratio between the shear stress and the tensile stress to give us the tendency of the adhesive failure. And she could really conclude that zircot has a higher tendency of failure rather than catseram. Another model, but then it was a 3D, was to try to compare and think about an FE of shear versus torsion adhesive strength test for dental composites. Because we know that the shear tests today, they give us tensile response. And no test today is able, no mechanical testing today is able to bring us the information of the shear stress, apart from torsion. However, we still don't have a torsion test that is really reliable experimentally. So we went to FE to see if torsion results could give us some answers. And you could see that although we don't have colors, you can see that there are really concentrated stress in some side and another one on the other side. And here we have quite an uniform distribution of stress in ring shape for these models. So this is torsion, this is shear. So we need to find quickly a torsion test to have more response about adhesive interface. So just here to put it bigger, okay? So they could conclude, we could conclude from it that the torsion test actually has a higher influence of shear stress on the stress state at failure. And the region of stress concentration is always close to the interface. So this is the wire, as you can see. So here it's more distributed, which is good. Higher extension of the bonded area is subjected for the maximum principal stress. So we are actually testing the interface here and not only an edge of it. And then it's easier in standardization of stress distribution due to the lower sensitivity to this thickness variation for the adhesive layer, varied as well as to the lower influence of the elastic modulus of the composite cylinder, which is also good in comparison to the shear test, okay? And I'd like to invite you now for an FE journey with me, because we could go like 20 hours here showing how important and how diverse you could explore FE. However, I'd like to take you to a journey on how you think about FE when you are having a problem to solve. So let's take a problem that is the shrinkage stress. Okay, so first of all, we need to know what's the origin of these stresses at the interface of bonded restoration. So we have restoration debonding and cuspal deflection after shrinkage, one or another or both. Thinking of debonding, it can generate gaps, microleakage, and secondary carriers. Thinking of cuspal deflection and restoration debonding, both can lead to dental fracture. And all these together give us a hard time back home, right? Post-operative sensitivity. So how could we understand and stop and think about the factors affecting this? So one of the factors affecting the stress magnitude is the C factor, as people thought that higher the C factor, higher the stress. However, many authors, including me, have been saying, no, it's not the case. And you're going to know why. So a first step was made by Miguel and de la Macorra, saying that the volume plays a greater role rather than the C factor. So the shape of it is not the only, the cavity design is not the only factor responsible for the tension, but also the volume has an important role. So save this information. Going forward, by studying the influence of these cavity dimensions in volume and C factor after shrinkage, what we've got was that similar volumes got higher C factors, higher fringe orders at internal angles. So when we say higher fringe, it's closer to the red color in the fringe. Similar C factors, higher volumes, higher fringe orders. So cavity depth was found to have a stronger influence than diameter on both response. So we have one thing that we need to pay more attention rather than only the C factor. Going forward, we had a little bit more information after working together. So we are a team made by the University of São Paulo here. I was in Birmingham working with William Paling at that time. And yeah, Braga is University of São Paulo as well. So we've done a very simple model again, that the software understood it's a cavity, it's a 3D, but we built a 2D, we call 2D axis symmetric model. So the software has the 3D interpretation. So with that model, we found that the structural stiffness affect the shrinkage stress at the tools present composite interface in bonded restoration. And again, an information about deep restorations. They are always problematic because they showed higher shear stresses. And up to date, we have no way experimentally to measure shear stresses. You can say, Fla, but there is the shear test. But the shear test, they measure tensile, not shear. Unfortunately, the amount of shear that they have, it's really, really tiny, and you only can detect it by finite element analysis, because you can ask, I want you to show me only tensile. I want you to show me only shear. But you cannot look at your sample and your computer, your Excel file, and ask that, or your universal testing machine. They will show you the final strength, and the final strength is unfortunately only tensile. So more factors, we've continued studying this. We've looked at, okay, not the C factor itself, but the shape influences, the volume influences. Then we discovered that the mechanical loading influences, but not only the presence of it, but the magnitude and the application, if it's concentrated or distributed, if it's just in a point or if it's like a pressure. Also, the properties of the material, like elastic modulus and Poisson ratio, influences the final results and the stress concentration in a model and also in reality. And there is another concept that I'm not sure if everyone had contact with that, which is called compliance. We use this word for many other things, but in FE and in this type of experiment that we are talking about, the shrinkage one, the compliance is calculated by the change in dimensions by the load that was applied. So here is a setup that Jack Ferracane did a lot, Roberto Braga did a lot, Leticia Boaro does a lot. That represents a tensilometer. So basically what it did, you put the composite here, and then
Professor Flavia, there is a bit disconnection. I think we face Professor Flavia. Yeah, I think she faced a little bit a bad connection. We just wait here. So at this time, if any of you guys have a question or something like this, we just put it until Professor Flavia is coming back again.
Can you hear me now? Hello?
Yes, this is much better. This is much better, Flavia.
Okay,
Yes.
I don't know what happened. I'm so sorry. It just
No
stopped.
problem at all. No problem
But I
at
was
all.
hearing you and I was seeing you. So this is why I really didn't know what happened.
No problem. No problem at all.
Can you see the presentation again and hear me?
Yes. Yes, we can see it. We can see it.
Okay, sorry about that again. So I was talking about this type of setup that it's about tensilometer, right? So basically you have here the light curing and you have this in a universal testing machine and the tensilometer here. And this is what send the computer the information. So you cure this and this composite is going to shrink. And then this system is going to have a feedback system to really measure how much shrinkage happened here. So actually it sends a displacement. So you can calculate the delta L. And of course you have the load from the calculation as well. So then finally you have the compliance. The only problem is that the compliance will be simulating a cavity, a type of cavity that has only two parallel walls. And in reality, in a tooth, we have this is parallel to this. The other one can be parallel to the other one.
شايفة فتح على طول في ثانية ازاي؟
We are ignoring what's happening with the pupil wall, for example, and also the relationship
هناك
of
العيال
this
بيحملوا ألعاب يا ماما النت
and
بيخلص
this
من أول
with this.
الشهر حرفيا
Sorry,
بيخلص من أول
I'm
أسبوع.
having interference from the others.
I'm sorry for
أيوة
confusion. في حد فاتح المايك بعد اذن حضراتكم؟
قاعدين ماسكين تباتهم عمالين يحملوا العاب.
يا دكاتره، بعد اسراء عبد الخالق بعد اذن حضرتك تقفلي بس المايك بعد اذن. I'm sorry for confusion.
No problem. So with that in mind, we had some answers in our mind. Do shrinkage stress vary in the same way as a function of the C factor in a tensilometer and in cavities? So I remember I was telling my supervisor and saying like, okay, we have all these questions and I feel like I'm a cat who would like to reach the moon. This is such a big question and I'm not sure we can answer just with the time we have. So he also believed. So I was like this, but we still work together and I still call him supervisor. I think it's like that with everyone, right? So we decided to study this first step. So we've built all these models that we want to vary the C factor and fix the volume, because if we have both together in the simulation, we couldn't answer which one is actually working or not. And you can say, oh, but there are some parts that is this one and this one and this one that is not actually very close to the clinics. But here we don't have to. Here the main thing is really to see which is the factor affecting the shrinkage stress generation. So we did it. The software understands all these cavities as this shape because we inform it's symmetric. So we don't need to draw everything. We just draw a quarter of it. And then this work is also published. And we have these pictures for the stress and these pictures for the strength. Again, I could spend 5-6 hours talking about this, but I'm going to concentrate in the part that we've got our answer. So first, we can see the red ones here, right? And a little bit more red here than on the other side. So let's take a look at these closely. We put some vectors to understand that when the composite is trying to shrink, so you can see the arrows going to this direction, okay, to the center of it. Can you see? And then the substrate goes to the other direction. And this is what causes this disturb at the interface. And then we thought, okay, if we have at the composite already this part that there is almost no stress, why don't we concentrate our studies and look at the corners and also at the smallest wall of the cavity? So when I say smallest, I say we have this. We're talking about this wall that is going to suffer more than this wall. And we usually clinically think on the other way around. So the first thing was, thanks gosh, we can reject that the stress increase with the C factor. You can see we've done a plot for each wall, and even though there is no science on it, okay, so the more you increase the C factor, it's not necessarily that you are increasing the stress. And then we've built it for each of the possible answers that we usually see in FE, and the same, very pure correlation. So the question in our mind after that was, okay, possible explanations. High compliance, predominance of volume effect. And we have done these models considering the volume constant. So let's play with the volume at some point. And then the geometry of the cavity, it's a cube. It has 5 walls. So it's different from what people have been found by using tensilometers. So it's okay. We are going in the right direction. So we started thinking of the volume in another way. Okay, the polymerization shrinkage stress depends upon wall stiffness, composite stiffness, shrinkage itself, but also the volume. But what do we mean by volume? Is that what everybody is considering? Is the whole volume of the restoration? We've seen that there are some parts in the resin with no stresses. So definitely not all the mass of the composite in the cavity is actually contributing for the stress generated in the cavity. So we need to look at it more carefully. And we named it provisionally as effective composite volume. Oops, yeah. So here, just to show, if I just plot the composite, the stress in it is not that big. The real stress is when I am really in contact with the walls, the cavity walls. So by looking at this picture, we thought, okay, we have to think about the whole body of the restoration, and we will end up having a shape close to a sphere cap, and then many spheres below it. So we can calculate how much volume is actually contributing to the shrinkage stress. So we don't need to go much further on it, but the formula of how to calculate the volume of this cap is the one that we've used here. So 1, 2, 3 caps, 1, 1. And we have here the height of the cap, the radius of the cap, and the radius of the whole sphere. So just to give you an example, for this cavity, we have a total of 20 cube millimeters, and we have effectively only 6.28